So when we left last time, we were discussing the centers in the brain that control respiration. So those are the apneustic and pneumotaxic centers in the pons, and of course the dorsal and ventral respiratory groups in the medulla oblongata. So I was discussing a little bit about these receptors and where they're located. So a lot of them are unsurprisingly located in your arteries because as we covered in the last Zoom session, hopefully I made it clear to you how close the link is between breathing and changes to your blood chemistry. And spoiler alert, that is what a lot of your last case study activity is about. So make sure that you're referring back to this information and the stuff about that in your book to successfully answer those questions. I'm giving you a little bit of a applied medical problem solving in that one. So keep in mind all of these structures here. Let me get my arrow. All these structures here are surrounded by cerebrospinal fluid. So in addition to receiving input from various peripheral sensors, there's also input in the form of detection of changes in pH and dissolved gas in the cerebrospinal fluid, because that comes from the blood, right? So if you see a drop in blood pH, for example, you would expect to also see a drop in CSF pH. So respiratory reflexes are basically ways that your autonomic nervous system primarily protects your respiratory system and helps you to breathe and change your breath patterns mostly involuntarily. So you have chemo and baroreceptor reflexes, and these are going to change the depth and rate of your breath in response to changes in blood pressure and also changes in blood chemistry. So between your brainstem and your lungs and your heart and your blood, there's this really robust communication. All of those systems are talking to each other all the time so that they are sort of marching in lockstep, so to speak. If they begin to have trouble communicating with one another, then you start to get problems with homeostatic feedback loops. And that's another thing that I address in the case study that I'm going to have you do. So hopefully that will help you sort of flex your thinking muscles about those topics and understand just how interconnected respiration and the cardiovascular system are. There's also protective reflexes. So for example, irritants in your airway. I think we've all sneezed or coughed when something nasty and irritating was in the air. I'm probably not alone in that I have some degree of seasonal allergies. So times of year like right now, going outside gives me irritant reflex action in the form of sneezing a lot. And there are others as well. So we have a diving reflex that is involved in putting your face in cold water, for example, and there are others. So peripheral chemoreceptors are going to monitor blood, partial pressure of oxygen, and pH. And then central chemoreceptors are primarily focused on carbon dioxide and pH. So remember, partial pressure of carbon dioxide in the blood is linked to pH changes, right? Because most of that CO2 that's coming out of your cells in metabolically active tissues is not staying CO2, it's getting converted into carbonic acid and becoming part of that buffer system. So really in the blood, pH and PCO2 are somewhat interchangeable, and your medulla oblongata has sensors for that stuff. So stimulation of the central chemoreceptors and the peripheral, but there's a stronger response from the central, causes an increase in rate and depth of ventilation. So I talked about Kussmaul respiration last lecture, and that's a change in breath pattern related to diabetic ketoacidosis. So this picture is just showing you the interlocking feedback loops. And I addressed these a little bit last time as well, just to point out both of them have a long and a short feedback loop. But regardless, the role of these feedback loops is to return arterial partial pressure of carbon dioxide to normal. Now, we think about PCO2 and carbon dioxide in general as being a waste gas, so it's a byproduct of metabolism. But notice that there's a homeostatic feedback loop involved in lower than normal arterial PCO2. So even though we're treating this gas as a waste, it's actually a problem if there's not enough of it. So your breathing will change, and your respiration will actually decrease due to medullary and pons control if you need to hold your breath a little bit to build up CO2 in your blood. So what all this means is really that although you do have peripheral oxygen sensors, because of the relationship chemically between oxygen and carbon dioxide, and because of carbon dioxide's effect on blood pH, those reflexes are actually more strongly tied to and more responsive to carbon dioxide and pH than they are to partial pressure of oxygen, which seems counterintuitive, but that's just the way it is, really. So just for reference, a 10% increase in partial pressure of carbon dioxide doubles respiration. It takes a 4 times bigger change in partial pressure of O2 to even change respiration by half. So that's a pretty big difference, and that should speak volumes about sensitivity of chemoreceptors and what specifically they're detecting. All right. So shallow water blackout is something that is good to be aware of. So this is an underwater faint during lack of oxygen to the brain. So that's obviously really dangerous, right? Because if there's any place you don't want to pass out, underwater is probably pretty high on the list. So this is due to lack of oxygen, obviously, from holding your breath for long periods of time. And it's difficult to recover because ordinarily your PCO2 would build up and the feedback loop tied to bringing PCO2 back down would kick in, and your dorsal respiratory group would fire, and then your pons would add increased time of inspiration and expiration to sort of correct that problem for you, whether or not you are conscious. If you're underwater, not the case. So obviously that's pretty bad, and it's something that it actually means that you can drown in relatively shallow water. So that's what it's referring to. And there's a question from somebody about deep water blackout. Well, shallow water refers to depths that normal people swim in without a self-contained underwater breathing apparatus. So generally speaking, you're not capable of blacking out in deep water unless you're scuba diving, and typically those situations tend to be more related to problems with, you know, your devices rather than your physiology. So, adaptation of chemoreceptors. Let's define this first. What I mean here is sensory adaptation. So not adaptation in the evolutionary sense, but we talked about this in 241, but I think it bears repeating because it's been a while since we discussed the idea of neural adaptation. So just to remind you, adaptation is when the nervous system stops paying attention to a prolonged stimulus over time. So a really easy to understand example of adaptation is smell. So the sense of smell is one of the fastest adapting senses. And that means that, like, maybe you walk into your house and you're like, well, this is what my house smells like to other people when they come here. And then, you know, within about 10 minutes, you're not actively smelling or noticing the odor of your house anymore. That's because the number of action potentials from your olfactory epithelium has been just turned down by your brain. So your brain takes the volume knob and turns it down because it's like, well, it's not really important to constantly be smelling this. This is also the #1 reason why sometimes people wear too much perfume because they can't smell themselves. Interestingly, and maladaptively, in people who are being ventilated by a machine, for example, adaptation of chemoreceptors means that the chemoreceptors will adapt to a signal that they should be paying attention to. So like long-term increases or decreases in PCO2 will stop being responded to by the medulla and the pons. So that's a real big issue. All right, baroreceptors, these are all about blood pressure, so making sure that your respiration is keeping up with your blood pressure and your cardiac output. And that makes sense, right? Because if your heart is beating really hard, typically that means that you are either exercising or there's a sympathetic nervous system event happening, which means that you're going to need increases in oxygen to keep up with the increased delivery of blood to your cells and tissues. So a temporary drop in blood pressure causes increased respiration unless sympathetic activation is occurring, and a temporary rise causes decreased. So this is in resting individuals. So think about laying down versus sitting up, changing postures, micro adjustments. Basically, the idea being that if your blood pressure rises slightly, the rate at which exchange is happening between your cells and tissues is going to change, so you want to decrease respiration to keep that chemistry steady. All right, Hering-Breuer reflexes. These ones are interesting. So these are related to the volume of lungs, and that's where those stretch receptors come in. So not baroreceptors in the arterial vasculature, but receptors in your lungs themselves. So we talked about pulmonary compliance and how you want your lungs to be kind of stretchy and easily expandable. But what you don't want is to overinflate your lungs such that your alveoli begin to get damaged. You also don't want to exhale so much that you are collapsing your alveoli. So both ends of the spectrum are potentially damaging for your lung tissue. So this is for tidal volumes greater than 1,000 milliliters. So if you think back to the tidal volumes chart, the number on that chart for normal tidal volume is about 500 milliliters. So this is twice that. So this is when you're taking real big, deep breaths in and out. So stretch receptors are basically detecting the degree to which you are stretching your airway and your alveoli. So the inflation reflex stops inhalation, and you can test this yourself. Just try to inhale as much as you possibly can and then keep going. You'll find that you can't. That's one of these reflexes. And same with the deflation reflex. So this basically just helps protect your lung tissue during forced breathing activities, like, for example, panting a bunch during exercise. All right, respiratory reflexes. There's protective ones, obviously, sneezing and coughing. These are for getting stuff out of your airway. There are others as well. So pain and other sort of stretching, so visceral stretching, etc. Those are going to change your breathing. Nice thing about this one, though, is that turns out there's a converse, there's another side to this, and that is that because of pain changing respiration, respiration actually feeds back on pain and can help one deal with and weather pain a little bit better. So this is why deep breathing exercises for things like labor and delivery can be helpful. And then, of course, voluntary control as well. All right, and that's the end of respiratory system. So now we get to start digestion.